Welcome back to the lecture series on 8085 microprocessor. In this lecture, we'll be discussing the number system that we'll be using for the entire course, as well as we'll also be discussing the 2's complement representation of negative numbers, what are its advantages and disadvantages, etc. Now, the number system that we'll be using throughout this course is going to be hexadecimal number system. We'll be using binary numbers and the corresponding hexadecimal numbers. Now, there is a reason why we use it. The reason is that the binary numbers, if you take 8 bits of binary numbers, 4 digits can be exactly represented as a hexadecimal number. That is the major advantage over here. Let's look at this. Let's say the binary 4 digits starts from 0000. It goes all the way up to 1111, which in hexadecimal will start from 0 all the way up to FF. Now, that is the advantage of using binary hexadecimal numbers to represent each 4 digits of binary numbers. So here there are 2 nibbles. So there will be 2 hexadecimal digits. This is 1001, 1001. Now, how to calculate the corresponding hexadecimal numbers? You just have to put 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Now, what is 2 to the power 3? 2 to the power 3 is 8, 2 to the power 2 is 4, 2 to the power 1 is 2, and 2 to the power 0 is 1. So, if you want to calculate what is this hexadecimal number, you need to add all the ones. Now, here in the 2 to the power 3 portion there is a 1, 2 to the power 2 portion there is a 1, and 2 to the power 0 portion there is a 1. So you just have to add 8 plus 4 plus 1, which is 8 plus 4 is 12 plus 1 is 13. 13 in hexadecimal number is D. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F, 1111 is 15. Now 10 in hexadecimal corresponds to 16 in decimal number. I hope this is clear. Now here it is 2 to the power 3 portion plus 2 to the power 0th portion, which is 8 plus 1, that is 9. So this is how we will be representing the binary numbers. We'll always be representing all the binary numbers in hexadecimal numbers. So that is the advantage of using hexadecimal numbers. Now, what is the advantage of using 2's complement form? Now, that's a very important question. In 8085 we can do signed operations or unsigned operations. Now, for doing signed operations, the 8-bit range is from minus 128 to plus 127. This is the range of 8-bit numbers in 8-bit signed numbers. For unsigned numbers, you can go from, if you're not interested with the sign of the numbers, you can go all the way from 0 to 255, right? Which is 0 to 255, which is 00 in hexadecimal to FF in hexadecimal, which is 255. These are basically 256 combinations, because 2 to the power 8, because we are dealing with 8-bit numbers. 2 to the power 8 is 256. 0 including 0, there are 256 combinations, 0 to 255. In hexadecimal, the corresponding numbers will be from 00 to FF. If we are dealing with signed numbers, then the range is constrained between minus 128 to plus 127. Now, always all microprocessors use 2's complement form to represent these numbers. there is a very huge advantage of using 2's complement form. We'll be looking at those advantages right now. Now, I hope you know what is the 2's complement representation of numbers. Now, if you want to represent a number in the 2's complement form, let's say you want to 2's complement form is basically for representing negative numbers, and let's say you want to represent a number, let's say 33. Now 33, how to represent 33 in 2's complement form? Now for representing 33 in 2's complement form, first you need to know these are all hexadecimal numbers. 33H. So 33H can be represented as 0011, which is the first 3, and the second hexadecimal digit can be written as 0011, which is the second 3, this 3. So 33, this is positive 33. To find its 2's complement form, its corresponding negative 33, you need to first take the 1's complement. Now 1's complement is basically reversing the digits or complementing each bits. Now if you complement each bit from 0011, 0011, you will get it as 11001100, and then you need to add 1 to it. Add 1 to the entire number, you will get it as 10110011. So this is the 2's complement representation of minus 33. I hope this is clear. Now there is also a easier method for finding the 2's complement form. So that is by looking from the right. If you look from the right onto the number, you can copy all the digits up to the first one. Here in this case, the first one comes in the first digit itself. Otherwise, you could have copied the entire number up to the first one, and here, since it is the first digit, you will have to copy only up to the first number, which is 1, and then you can reverse all the other digits. Now if you reverse all the other digits, you will get this. Next is 1, which becomes 0. The next is 2 zeros, which you will write it as 1 1, and then there are 2 1s, which is going to be 2 zeros, and then you have 2 zeros, which will be reversed as 1 1. So this is an easier method for finding the 2's complement. Copy all the numbers till the first one. Here in this case, the first digit itself is 1. Otherwise, if there were zeros, we would have copied all those zeros up till the first one, and then we would have inverted all the other digits in the left hand side of the first one. So here the first one was copied, and then all the other digits were inverted from the original number, which is same as the 2's complement form. Whichever is easy for you, you can choose that. No compulsions which method you want to follow, it's up to you. Now let's look at this simple subtraction. Now 33 minus 47. Now whenever you subtract a larger number from a smaller number, you will get a negative number. 33 minus 47. Let's look at its binary equivalence. Now 33 is 0011 and 0011. Always remember, we are only talking about hexadecimal numbers. This is 33H, this is 47H. Hexadecimal. H stands for hexadecimal number. Now 4 is 0100, and 7 is 0111. Now let's subtract these two numbers. When we subtract these two numbers, what we get is that 1 minus 1, you will get it as 0. 1 minus 1, you will get it as 0. 0 minus 1, you will have to take a borrow from over here. So this becomes 0, this becomes 1, this becomes 1 0. So 1 0 minus 1 is 1. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 0 is 1. Now here again we need to take a borrow. since there are no ones, we assume that there is a 1 over here. We cut that 1 from here, put this 1 over here and this 1 over here, so this becomes 1 and this becomes 1. Now this is the answer that you get when you subtract 33 minus 47. Now this is in the 2's complement form. What should be the actual answer over here? If you reverse it, you will get the actual answer. 47 minus 33 would be 414 minus 14 minus 14 should be the answer. So let's see whether we got the same answer over here. Now always we get the result, if the result is negative, we get the result in 2's complement form. That is what we discussed just now. So here, how do we find whether the number is positive or negative? The first thing that you have to look is the most significant bit, MSB. This is your MSB, most significant bit. If the MSB is 1, it means that your result is negative. So here, if you look at this result, the MSB is 1, the result is negative. To get the original number, you will have to take its 2's complement. Like the way we took 2's complement over here, we will have to take the 2's complement to see what is the actual number. So let's take the 2's complement. You get the result as, let's take the first, here if you apply the rule that we applied over here by taking all the numbers till the first one. Let's do this exercise in this one. Let's copy all the numbers till first one. So you will get the result as 0 0 1. We have copied all the numbers till the first one from the right. Now all the other numbers we are going to invert. So if we invert them, 1 becomes 0, 0 becomes 1, 1 becomes 0. You get 3 more zeros. So you get it as, this is 1 digit, this is another digit, this is 1, this is 4. So you got the actual result. So this is the advantage of 2's complement form. When you subtract a larger number from a smaller number, you will directly get it in the 2's complement form. Now another way for doing this same arithmetic is that either you can subtract 33 minus 47 like this, in this fashion. We took this as a positive number 33, 47 also as a positive number, and we subtracted 47 from 33. Or we can do one thing, we can add these two numbers, 33 plus minus 47. Now what is minus 47? For getting minus 47, you have to take the 2's complement of this number. So if you take the 2's complement of you have to take the 2's complement of 47, that is minus 47. So the 2's complement of 47 is, you go from the right to the first one. If you go from right to the first one, the first digit itself is the first one, so you get it as 1. Then all the other numbers you will going to invert. So the next two are 2 ones, you will get it as 0 0, and then you have a 0 which makes it 1, 0 0 becomes 1, and then there is a 1 which becomes 0, and then a 1. This is minus 47. Minus 47 is in 2's complement form looks like this. And then we are going to add what? We are going to add 33. 33, if you add, you will get it. What is 33? 33 is 0 0 1 1 and 0 0 1 1. If you add these two numbers, you will get it as 1 plus 1 1 0, 1 plus 1 1 0. You get it as 1. You get it as 1. 1 plus 1 0 1. 1 plus 1 1 and 1 carry, and then you get 0 plus 0 plus 1, which is 1, and then you get 1, which is same as your result over here. So this is since when you look at the MSB, if it is 1, it means that the number is negative, it is in the 2's complement form. You take the 2's complement of this number, you get the positive number, corresponding positive number. So this is a negative number, which is same as your number over here. So this is the advantage of using 2's complement form. Now we can also look at one more example. This is a very interesting example over here. So let's say you want to subtract 16-bit data. Now these are all hexadecimal numbers. So we are going to subtract a 16-bit data from another 16-bit data, 4926 minus 3265. Right? Here we are going to subtract these two 16-bit data. Now whenever your microprocessor subtracts data, 8085 is a 8-bit processor and it can subtract only 8 bits at a time. So let's follow the same process over here and let's subtract 8 bits at a time. So 26. Now what is 26? 26 is 0 0 1 0, 6 is 0 1 1 0. Now what is 6b? 6b is going to be 0 1 1 0. B is 11. 11 is 8 plus 2 plus 1, that is going to be 1 0 1 1. So when you subtract these two numbers, 26 minus 6b, you will get it as, if you subtract, you will get it as let's look at what is the result that you are going to get. 1 minus 0 minus 1, you have to take a borrow from here. This becomes 0, this becomes 1, 1 0, the result becomes 1. Then again 0 minus 1, you will have to take a borrow from here. This becomes 0, this becomes 1 0, 1 0 minus 1 is 1. Again this 0 minus 0 is 0, 0 minus 1 is going to be, again you will have to take one borrow. This becomes 1, this becomes 1 0, 1 0 minus 1 is 1, 1 minus 0 is 1. Again we have to assume, we have to take one borrow from over here, and then we'll give this as 1, this as 1, and this as 1 0. So you'll get the result as 1 0 minus 1 is 1, 1 minus 1 is 0, and 1 minus 0 is 1. Now at present, let's say if you're stopping the subtraction process, then your answer is going to be negative. Why? Because you have subtracted a larger number from a smaller number. So your MSB shows that your result is negative in case if you are stopping the subtraction at this point. If the processor, if you only were doing a 8-bit subtraction process, then your result would have been negative. You would get the result by taking the 2's complement of this. Let's look at what is the result. Let's take the 2's complement from here, since it is a negative number. So you will get it as 1 0 1 0 0 0 1 0. That's the 2's complement form. This is the result is 4, and this is 4 plus 1 5. So your result is going to be 45. 45 is your answer. Now B is 11. 11 minus 6 is 5. 6 minus 2 is 4. Yeah, you have got the right result. That's going to be minus 45. So this is the 2's complement representation of minus 45. This would have been your result if you would have stopped the subtraction process at this point. Now this borrow that you have taken goes into a flag. Now we'll be discussing the flag in this same lecture. This goes into a flag known as your carry flag. Whenever there is a carry out, let's say if you are doing a addition, here we are doing a subtraction. If there is a carry from the last bit, from the MSB, if there is a carry, it goes into the carry flag. Also, if there is a borrow from the MSB, for the MSB or the other if at all there is a borrow that is taken for the 8 bits over here, then this borrow also comes from the carry flag, or it goes into the carry flag. The carry flag will be set to 1 if you have borrowed 1, assuming that there is a 1 over here. So if you would have stopped the calculation at this point, you would have got the result as minus 45. Since you are going to do a 16-bit operation, let's see what the result comes out to be. Now here there is a borrow, the borrow is 1. Now the next 8-bit is 49 and 32. Now what is 49? 49 is 4 is 0 1 0 0, and 9 is 1 0 0 1, and 32, we need to subtract these two numbers. 32 is 3 is 0 0 1 1, and 2 is 0 0 1 0. Now if you subtract these two numbers, you will get the result as, here 1 minus 0 is 1, 0 minus 1, you have to take borrow from here, 0 1 1 0. So 1 0 minus 1 is 1, 1 minus 0 is 1, 0 minus 0 is 0, 0 minus 1 is, you need to take a borrow over here, this becomes 0, this becomes 1, this becomes 1 0, 1 0 minus 1 is 1, 1 minus 1 is 0 0 0. So you get the result as, this is 1, this is 7, the MSB is 0, which shows that the result is positive. So your result is 1 7, and over here your result is, now what is this number? This 4, these 4 bit is 8 plus 2 10 plus 1 11, which is B, and this is again 8 plus 2 plus 1 11, which is B. So you get the result as 17 BB, which is your 8-bit result, which is a positive number. So we need to subtract the borrow as well from this bit. So if you want to if you have to subtract the borrow, then that will be subtracted from the 17 minus 1, which makes the entire result as 16 BP. Right, so the result is it's not 17 BB, it's 16 BB will be the actual result, since there is a borrow as well. There is a borrow that you have taken, assuming that it's a 16-bit number, you have taken a borrow from here, so you need to subtract that as well from the first bit. So that makes it 16 BB, that is your final answer. So this is a positive number. In case you would have stopped at this point, the result would have been different, but here the result is different. That is the advantage of using 2's complement form. Both the ways you will get the actual result, the right result. So that is the major advantage of using 2's complement form in 8085 or in any other processor. Now let's look at the various flags of 8085 microprocessor. In the previous lecture we discussed that there is a register known as the flag register. In the architecture of 8085 we saw that there is a register which is known as the flag register. Now what does flag register stores? It stores the current status of result. Now with status of result, so with every arithmetic operation your flag register is going to get updated. Let's say you did an operation, let's say 45 plus 39, you got a result. Again you added some other value with 54, again you get a result. You get a result over here. So at this point, let's say again after that, let's say you got another, you took another two numbers, 39 minus 25, again you got a result. So at all these points, each and every time, what happens? These flag registers are going to get updated corresponding to your results that you get in your arithmetic operations. So what does the flag register have? It has the current status of the result. The moment you do another arithmetic operation, the previous status of result is already gone. Now you will have the result, the status of the current result. Now status means what? Status means what is the status of your result. Now status of your result means let's say whether there is a carry out from your result. When you added two 8-bit numbers, did you get a result with 9 bits? That is what is known as carry, right? Let's say you added two 8-bit numbers and you got a result of 9 bits. Now your accumulator can only store 8 bits. Now where will you store the 9th bit? Now that bit will go into your carry flag. Now carry flag will be set to 1. Now CY stands for carry. CY stands for carry flag. Whenever your result has, whenever you do an arithmetic operation like addition or a subtraction, if there is a carry from your 8th bit, let's say, let's look at one simple example. Let's add FF plus FF. Now what is FF? FF is 1 1 1 1 1 1 1 1, and what is again 1 1 1 1 1 1 1 1. If you add these two numbers, this is the maximum two numbers that you can add. So when you add these two numbers, you get 1 plus 1 0, there is a carry 1, 1 plus 1 0 plus 1, that is going to be 1, again there is a carry 1 plus 1 0, 1 plus 1, you get 1, 1, again there will be a carry 1 plus 1 0, again plus 1 1, again there is a carry 1 plus 1 0 plus 1 1, carry 1, carry 1, carry, again 1 plus 1 0 plus 1 is 1, again there is a carry. Now this carry should come over here, but since your accumulator is of 8 bits, your accumulator will only store these 8 bits. This is F, this is E. Your accumulator will have the result FE. Accumulator is the register which stores the result. You will get the result FE, but the actual result is 1 FE. Now this 1 will be stored in your carry flag. This is the carry out from the most significant bit, this is the most significant bit. From here you have a carry out which will be stored into your carry flag. Similarly, when you're doing a subtraction, in the previous case we already saw, in the previous case when we did subtraction over here, we already saw that there is a borrow that we take from the next 8 bits. This borrow will also go into your carry flag. In case you take a borrow, it is going to be there in your carry flag. It will be stored in your carry flag. It will be, your carry flag will be set to 1, which represent either there is a carry out from the MSB or there is a borrow that you have taken. Now let's look at the other flags. Now the next flag here is P. Now these are the different bits, D0 to D7. It's a 8-bit register. These bits D1, D3 and D5, D1, D3 and D5, these bits are not used. These bits are not used in the carry flag, in the flag register. Rest all the bits are used. This CY stands for carry, P stands for parity, AC stands for auxiliary carry, 0 stands for 0 flag, and sign S stands for sign flag. So carry flag, I hope it's very clear. Now let's look at parity flag. Parity flag. Now parity flag tells the number of ones in your result. Let's look at this result. In this result there are 7 ones, which means the parity is odd. In your accumulator, what is the number of ones that you get in your result? That is what your parity flags tells. Now, so whenever there is even number of ones, if there are even number of ones, your parity flag will be set to 1. It will be set to 1 if there are even number of ones. Now the parity flag for 8051 is different. In 8051 the parity flag will be set to 1 for odd number of ones. Here for even number of ones parity flag is set to 1, and parity flag will be set to 0 if you have odd number of ones. Odd number of ones, you will have the parity flag to be set as 0 for odd number of ones. For even number of ones it will be set to 1. That is the function of parity flag. Now auxiliary carry. What is auxiliary carry? AC stands for auxiliary carry. Now it is very similar to your carry flag. Only difference is that whenever there is carry from your lower nibble to your higher nibble, if there is a carry from your lower nibble, this is your lower nibble 4 bits, this is your higher nibble of 4 bits. If there is a carry from your lower nibble to your higher nibble, your auxiliary carry flag will be set to 1. That is what is your auxiliary carry flag. Then comes your 0 flag. Now if the result, if whenever you do an operation, if your result is 0, if your result is 0, this flag will be set to 1, indicating that your result is 0. Now, there is a small confusion. There could be a small confusion. What is 0 flag? 0 flag tells whether your result is 0. How does it tells? By setting itself to 1, not by setting itself to 0, by setting itself to 1. Whenever your result of an arithmetic operation, let's say you are doing an arithmetic operation, let's say you are doing a subtraction, let's say you do 43 minus 43, right? If you are doing 43 minus 43, your result will be 0 0, and if the result is 0 0, your 0 flag will be set to 1. Otherwise it will be set to 0. Whenever, only when your result is 0, it will be set to 0. All the other times your 0 flag will always be, it will be set to 1. All the other times your 0 flag will be 1. Now comes a very interesting flag, which is known as your sign flag. Sign flag. Now it is very obvious that sign flag will tell the sign of your result, whether the result is positive or negative. Now if sign flag shows if sign flag is set to 1, it means that your result is negative. If sign flag is set to 0, it means that your result is positive. Now in 8085, the major flaw of 8085 is the way in which they have designed its sign flag. Now let's look at the functioning of this sign flag. Now sign flag actually copies just the most significant bit, MSB of your sign, MSB of your result. Now it just copies the MSB of your result. Now if this MSB is 1, it just copies it as 1, and it gives a result that it gives the idea that the result is negative. And if the MSB is 0, it copies the 0 and it gives the result as positive. Now there is a problem here. The problem is that, let's say you are working with sign numbers. So in the beginning of the lecture we already discussed what is the range of sign numbers, 8-bit sign numbers. So let's go back to that point. So we discussed here the range of sign numbers is from -128 to +127. This is the range of sign numbers. In this 128 and 127 are decimal. In hexadecimal it's from in hexadecimal it will be from let's look at what is -128. It is -80. -80 is again in 2's complement form will be 1000 0 0 0 0. If you take the 2's complement, it is again going to be 80 itself. So your range in 2's complement form, this range can be written as minus 80, can be written as 80 to 7f. 127 is 7f, which is 0 1 1 1, f is 1 1 1 1. If it's a bit confusing to you guys, don't worry, it is very simple. The range is in decimal, it is from minus 128 to 0 in the negative side, and from 0 to 127 in positive side. Now whenever, if you go beyond this range, if you go beyond these values, then you will end up getting wrong results. It is your responsibility to make sure that you are well within the range always. If you go beyond this range of minus 128 to plus 127, you will definitely get a wrong result. Now this is the major flaw of 8085 microprocessor for when it has created its flag registers. Now we already discussed that the flag register, the sign flag, is going to copy the MSB of the result. Now if the MSB of the result is 1, it indicates, we already discussed that the MSB of a result is what indicates whether the number is positive or negative. Let's say you got a result 101101110. This is your result. Now first thing you look is your MSB. If the MSB is 1, it means that if you're working with sign numbers, it means that your result is negative, and therefore your sign is going to be negative. The same thing will be copied into your sign flag. The sign flag will copy the same value of the MSB, and it will put the value as 1, indicating that the result is negative. If the result was, let's say if the result was, when you added two numbers, you got a result 0 1 0 1 0 1 1 1. Right now here the MSB is 0, which means that the result is positive. So this is what will be copied into your sign flag. Now the problem is that, let's say you go out of this range of the sign numbers. Let's say you are adding two numbers, two hexadecimal numbers, 64 and 43. Now we already discussed that in hexadecimal numbers the range is from minus 80 to 7f. In the hexadecimal numbers, in decimal numbers, minus 128 to plus 127 is the range. So it's definitely going to go out of the range. 64 plus 43 will definitely go out of 7f. Now let's look at these numbers. Let's look at what is 64. 64 is 0 1 1 0, 4 is 0 1 0 0, 43 is going to be 0 1 0 0, 3 is 0 0 1 1. When you add these two numbers, you will get 1 1 1 0 0 1 1 0 1 1. Right now this is your result. 1 0 1 0 0 1 1 is your result. Now when you look at this result, when the first thing that you'll be looking at is your MSB. Now your MSB is 1, which will be stored into your sign flag. What does it indicate? It indicates that your result is negative, but you added two positive numbers. You added 64 and 43, but you got a result as a negative number. This case only applies whenever you are working with signed numbers. In case if you are working with unsigned numbers, you don't look at the MSB and you don't look at the sign flag also. But since, let's say you are working with signed numbers and you added these two numbers, you went out of the range of 127 or 7f in hexadecimal, you get a wrong result. Now in 8086, this is indicated using a flag known as overflow flag. Now this problem was rectified in the processor 8086 processor, but 8085 had this major issue that it could give a wrong result if whenever you went out of your range of signed numbers. Now that is a problem that has been rectified in the next version of 8086 of Intel processors. Now this is a problem. You may not find this detail in most of the resources, but this was a major flaw of 8085. So this explains what is your different flags. Now let's just go through a quick recap of the flags. Now here we discussed which are the different flags. There are 5 different flags: sign flag, zero flag, auxiliary carry flag, parity flag, and your carry flag. Now carry flag stands for whenever there is a carry out from your MSB, from the most significant bit, it goes into your carry flag. Or if there is a borrow, that also goes into your carry flag. If you're subtracting a larger number from a smaller number, definitely there would be a borrow out, and that borrow will go into your carry flag. Now what is parity? Parity stands for the number of ones. If there are even number of ones in your result, then your parity flag will be set to 1. If there are odd number of ones in your result, then your parity flag will be set to 0. Auxiliary carry: whenever there is a carry out from your lower nibble to your higher nibble, then there is a auxiliary carry. There will be auxiliary carry from the lower nibble to your higher nibble. That is known as your auxiliary carry flag. Then comes your zero flag. If at all your result is 0, then your zero flag will be set to 1. If your result is not 0, then your zero flag will be set to 0. Don't get confused. Then comes your sign flag. What the sign flag does? It just copies the MSB of your result. Whatever is the MSB, it directly copies into your sign flag. If the MSB is 1, it copies into the result and it gives the result as the result is negative. If the sign flag, if your MSB of the result is 0, it shows that your result is positive. Now this only applies whenever you are working with unsigned, whenever you are working with signed numbers. The processor doesn't know whether you are working with signed numbers or unsigned numbers. It always copies the MSB of your result. It doesn't check whether you are working with signed numbers or unsigned numbers. Neither we tell the processor that we are working with signed or unsigned numbers. So the processor will always copy the MSB of your result. It is our duty whether we want to check the sign flag or not. Second problem is that whenever you do arithmetic operations in 8085, you need to make sure that you don't go out of the range of signed numbers. If you go out of the range of signed numbers, definitely there will be an overflow and your sign will be wrong. You will get the opposite sign of the actual result. We also looked at a small example over here. When we added 64 plus 43, the result should have been positive, but you got the result as negative. That is because there is an overflow. Overflow means you are going out of the range of 7f or in decimal 1 plus 127. You are going out of this range. If you go out of this range, you will definitely end up getting a opposite sign. In 8085, we don't have an overflow flag, and therefore we won't be able to understand it from the sign flag whether we have overflown or not. That is a major flaw of 8085, which has been rectified in 8086 by putting an overflow flag. So in 8086, whenever you check the result, whenever you check the sign of the result, you can also check the overflow flag, thereby confirming that your result is actually right. But that option is not there in 8085 microprocessor. You have to go with the sign flag, and it could be wrong as well. Yeah, so that is the that ends our today's lecture.